Welcome back to the deep dive. Today we're looking at something that sounds almost positive, but is actually pretty devastating for our waterways.
That's right. We're talking about eutrophication.
Trophication. Yeah, I've definitely seen, ponds or lakes suddenly go green and murky. Sometimes they even smell bad. Is that what this is?
That's exactly it. It's basically overfeeding a body of water until it collapses. Sounds strange, doesn't it?
It really does. So our mission today is to, unpack this whole process.
Precisely. We want to give you, the learner, a clear step-by-step understanding. We'll define it, figure out where the food comes from, and then trace the chain reaction that leads to ecological disaster.
Okay, let's start with the name itself. Eutrophication. You said overfeeding. Does the name hint at that?
It does. It comes from Greek, meaning well-fed or well-nourished.
See, that sounds great. If I'm a plant living in a lake, being well-fed seems like a good thing.
You think so? But it's a classic case of too much of a good thing becoming toxic. Eutrophication specifically refers to when large amounts of inorganic mineral ions flood into a body of water.
Inorganic mineral ions. Like what specifically?
We're mainly talking about nitrates and phosphates.
Yeah.
These are essential nutrients, yes, but in excess, they trigger harmful effects throughout the whole aquatic ecosystem.
Why the emphasis on inorganic ions? Is that important? Does it make a difference compared to just, general nutrients?
Oh, absolutely. It's crucial, particularly regarding how fast things happen. Inorganic ions are simple chemical structures, almost like salts.
Okay.
They dissolve easily and become instantly available for things like algae to use. It's like giving them a sudden, massive sugar rush, which kicks off the whole problematic sequence we're about to describe.
Got it. So it's like readily available fast food for algae. Where is this huge overload of nitrates and phosphates actually coming from? Are we just dumping this stuff into rivers?
Well, sometimes yes, unfortunately. The source material points to two main culprits. First, there's waste.
Like sewage.
Exactly. Untreated sewage is obviously a big problem, packed with nitrogen and phosphorus. But even treated sewage can still contain significant amounts.
Okay, that makes sense. Waste has nutrients. What's the other major source? You mentioned two.
The second one, and often the bigger issue, especially near farmland, is agriculture. Specifically, artificial nitrate and phosphate fertilizers.
Ah, the stuff farmers put on fields to help crops grow.
Precisely. When you have large-scale farming using these artificial fertilizers, nearby rivers and streams often end up with really high concentrations of these ions.
But hang on, isn't fertilizer supposed to stay in the soil for the crops? Why does so much of it end up washing into the water, especially the artificial kind?
It really comes down to solubility. This is key. Let's take nitrates first. Artificial nitrate fertilizers are highly soluble in water.
Meaning they dissolve very easily.
Very easily. Think of stirring salt or sugar into water. It just disappears, dissolves right in. So when it rains heavily on fields treated with these fertilizers.
The rain just washes the dissolved nitrates straight out of the soil.
Exactly. It gets washed through the soil profile. That's the process called leaching. The dissolved nitrates seep down with the rainwater into groundwater or run directly into ditches and streams.
Right, leaching. So it's not just flowing over the surface, it's actually pulled down through the soil itself because it dissolves so well.
Precisely. It's almost unavoidable with these highly soluble artificial forms. Now, phosphates are a little different.
Okay.
Artificial phosphate fertilizers are generally less soluble than the nitrates, so leaching isn't quite as big an issue for phosphates.
But they still get into the water.
Oh, yes. They tend to get washed into waterways more by surface runoff. Imagine heavy rain washing loose soil particles, which have phosphate attached to them, directly off the surface of the field and into the nearest stream.
So nitrates leach through the soil, phosphates wash over it, both end up in the water.
That's a good way to put it. And here's an important contrast, thinking about solutions maybe. This kind of rapid, problematic eutrophication is actually less likely if farmers use organic fertilizer.
Like manure.
Yes, like manure or compost.
Why is that better for the water? Doesn't manure also have nitrogen and phosphorus?
It does, but the crucial difference is that the nitrogen and phosphorus compounds in manure are organic. They're part of complex molecules.
Ah, so not simple inorganic salts.
Exactly. These complex organic compounds are much less soluble. They don't just dissolve instantly in water, they tend to bind more strongly to the soil particles.
Meaning they don't wash away nearly as easily.
Correct. The nutrients are released much more slowly as the organic matter decomposes. This is good for the crops, giving them a steady supply, and it's much better for nearby water bodies because you don't get that sudden, massive influx of soluble ions.
That makes a lot of sense. Slow release versus a sudden flood. Okay, so you've got the fuel, identified these excess soluble inorganic minerals pouring into the water. Now, let's get to the chain reaction. What's the very first thing we'd see happening?
The first visible sign is growth, explosive growth. These excess minerals act like rocket fuel for algae and sometimes other microscopic organisms like cyanobacteria.
This is the algal bloom.
This is the algal bloom. You get a massive, rapid increase in their population. It can become so dense it forms a thick, visible scum right on the water surface. Think of pea soup, but covering a whole pond or lake area.
Right, I've seen pictures. It's not just a slate green tint, it's a proper layer.
A thick layer, yes. And the scum immediately causes big problems for the life underneath it. It kicks off the destructive cascade in two main ways.
Okay, what's the first impact?
Light blockage. That thick scum acts like a blanket, preventing sunlight from penetrating down into the water.
And that's bad
For the rooted plants growing on the bottom. Plants like, pondweed. These plants are vital in a healthy system because they perform photosynthesis.
which produces oxygen.
Exactly. Photosynthesis releases oxygen into the water, which fish and other organisms need. But if sunlight can't reach them because of the algal scum,
They can't photosynthesize. Oxygen production plummets.
it drops off dramatically.
Yeah.
So the oxygen supply starts to dwindle. That's problem number one.
Okay, so less oxygen coming in. What else is happening? Does the algae itself cause issues beyond just blocking light?
Yes, because the bloom can't last forever. The algae multiplies so fast they use up the readily available nutrients, or they simply become too dense and block their own light. So fairly quickly, the algae start to die off in massive numbers.
Ah, so now you have this huge amount of dead algae sinking down through the water.
Correct. A massive load of dead organic matter. And something has to break that down.
Decomposition. Who does that job?
Primarily, it's the aerobic bacteria that naturally live in the water.
Hmm.
They're the decomposers.
Aerobic meaning they need oxygen.
Yes, and this is where it gets really bad. These bacteria respire aerobically as they break down all that dead algae.
Wait, so the oxygen supply is already falling because the rooted plants aren't getting light?
Uh-huh.
And now the bacteria cleaning up the dead algae are using up what little oxygen is left.
Precisely. You have a massive increase in oxygen consumption by these decomposer bacteria, happening at the exact same time as the main oxygen production has basically stopped.
Wow, okay. That sounds like a recipe for disaster.
It is. The decomposition of that huge algal mass consumes the dissolved oxygen in the water incredibly rapidly, much faster than oxygen can diffuse in from the air at the surface. This is the core mechanism. It creates oxygen-depleted zones, sometimes called dead zones.
Like the big one in the Gulf of Mexico people talk about.
Exactly like that. It's driven by this same process, often fueled by nutrient runoff from the Mississippi River Basin. It's a huge, real-world example.
That really drives it home. So with oxygen levels crashing, the outcome seems inevitable for anything that breathes.
It is. The low oxygen levels, technically called hypoxia, make it impossible for fish, aquatic insects, crustaceans, basically any aerobic animal to respire properly.
They suffocate.
They suffocate and die. And tragically, their dead bodies then add even more organic matter to the system.
Which fuels even more decomposition by the aerobic bacteria, using up even more oxygen. It's a vicious cycle.
A complete cascading failure, all triggered by that initial overload of nutrients. And in really severe cases, it doesn't just stop at low oxygen. It can go all the way.
All the way to what? What's the final stage?
The water can become anoxic.
Anoxic, meaning
Virtually zero dissolved oxygen left. At this point, the ecosystem as we knew it has completely collapsed. The fish are gone, the insects are gone, the rooted plants are dead.
That sounds truly awful. And you mentioned earlier, this is often when things start to smell really bad.
Yes, that's a key indicator. Because even with no oxygen, decomposition doesn't entirely stop. But the job gets taken over by different microbes.
Not the aerobic ones.
No, now it's the turn of anaerobic bacteria. These are organisms specialized to live and respire without oxygen.
Yeah.
And their metabolism produces very different byproducts.
Gases, right, foul-smelling ones.
That's right. You start to get gases like methane, which has that swampy gas smell, and very characteristically, hydrogen sulfide.
The rotten egg smell.
That's the one. When you smell hydrogen sulfide coming off a body of water, it's a strong chemical signal that the system is anoxic. It tells you that the dominant life forms are now these anaerobic bacteria.
So a simple input of fertilizer, something meant to boost life, can lead all the way to this this anoxic, smelly state where only anaerobic bacteria thrive.
It's a stark illustration of how interconnected these systems are. That initial nutrient input gets magnified through the bloom, the light blockage, the decomposition, the oxygen crash, ultimately flipping the entire biological community on its head.
It's quite a sequence. So for you, the learner, grappling with this, the key takeaway is really that step-by-step process. The soluble nutrients arriving,
Then the algal bloom exploding,
which blocks the light, killing the deeper plants and stopping oxygen input.
followed by the massive decomposition of dead algae by aerobic bacteria, which consumes all the remaining oxygen.
Leading to the death of fish and other aerobic life, and potentially that final anoxic state. Understanding that sequence explains the whole devastating impact.
It really does. It shows how human activities, like agriculture and waste disposal, can profoundly alter aquatic environments through this very specific biological mechanism.
And thinking about that final state,
Yeah.
you mentioned the smell, the hydrogen sulfide and methane. That smell isn't just unpleasant, it's a chemical signpost, isn't it?
Absolutely. It signals a fundamental shift.
Mm.
Aerobic life, which uses oxygen for respiration, a very efficient energy-yielding process, has been completely replaced by anaerobic life.
Which produces these smelly gases instead.
Right. And that brings up a fascinating final thought, something for you to ponder. Those aerobic organisms, like fish, got a lot of energy from using oxygen. The anaerobic bacteria that take over in anoxic conditions are clearly surviving, but they're producing things like hydrogen sulfide and methane. What kind of different, likely much less efficient energy pathways must they be using in that oxygen-free environment? How does their whole energy economy compare to the aerobic world they replaced?
A really interesting metabolic question to think about the energy cost of living without oxygen. That's a great place to leave it. Thank you for walking us through that complex process.
Nice pleasure.
And thank you for joining us for this deep dive. We'll catch you next time.